Hey guys, today we'll talk about the medchem of the calcium channel blockers, and as usual, any additional comments is for your own education. The reading objectives are first to describe the mechanism of action of the calcium channel blockers and understand how each of the three kinds, the dihydropyridines, verapamil, diltiazem, they bind to different allosteric binding sites at the calcium channel, and therefore they can interact actually with each other sometimes. They interact with each other. Basically, if you combine two of the calcium channel blockers, as you will see, then they can either enhance or inhibit each other's activity. And then compare between the heart rate, the effect of these blockers on the heart rate and the contractility. Basically, the chronotropic, which is the heart rate, and the inotropic effect, which is the force of the heart. As you will see, verapamil and diltiazem are able to decrease the contractility and the rate of the heart rate, basically. But with the dihydropyridines, they only cause, they do not affect the heart rate. In fact, they can actually increase that as a reflex effect. Okay, but both, in general, both classes, both kinds, or all of the calcium channel blockers are actually vasodilators. Okay. And then also make sure you can use the structure activity relationship information that we have, in particular how the position of the substitution at the ring, at the ring that's attached to C4. There is a substitution in this ring, so the position of this substitution can affect the activity. Basically, we want the two rings to be perpendicular to each other, and then to do that, then the substitution should be either on the ortho or the meta position, but not the para. So in the case of the para, the activity decreases significantly. And then explain the rationale for designing the clevidipine. Why is it designed in the ultra short, such that it has an ultra short duration of action? And then see the impact of the stereoisomerism of the verapamil on the dosage of the verapamil when it's given orally or parenterally. So verapamil is a stereoisomer. It has R and S. One of them is extensively metabolized, and therefore when it's given orally, we'll have to give higher dose. But when it's given, because the drug goes through the liver, it's extensively metabolized. But then when it's given by IV, then we don't have to give as much of the verapamil. And then explain why the verapamil and the nicardipine are incompatible with some of the IV solutions. Is actually the diltiazem as well, is in theory should be incompatible with the IV solutions. So explain why is that the case, and then appreciate the importance, or value the importance, of designing these calcium channel blockers in the sustained release form instead of the immediate release. Okay, why is that true? What happens if you give these products in an immediate release form? And then understand how these products affect or cause a lot of drug-drug interactions, mainly because they inhibit the CYP3A4. So they can cause a lot of interactions, besides the fact that they themselves interact with the grapefruit juice, which is an inhibitor to the CYP3A4. Okay. Let's start by a quick overview for the types of calcium channel blockers. There are basically three kinds, or two classes. One of them is the 1,4-dihydropyridines, and the other class is the non-dihydropyridine, which can be further classified into two kinds: phenylalkylamines and the benzodiazepine, and there's only one example on each one. So basically you have the 1,4-dihydropyridine, or for short 1,4-DHP, and the verapamil or diltiazem. So the 1,4-dihydropyridine from the name. This ring here is a pyridine, but since it's not completely aromatic ring, um, the position number 1 here, 2, 3, 4, 1 and 4 have been substituted with hydrogen, and that's why we call it 1,4-dihydropyridine. Anyway, so then we have the verapamil and the dialtism, and this one actually is no longer in the market, so just forget that example here. So despite the fact that they're called calcium channel blockers, you might think that these products simply plug the hole where the calcium flow the channel physically, but actually this is not how they work. I will explain this shortly. In fact, they bind to some specific sites at the receptor, which is called the L-type receptor. You probably have seen in the notes that there are 2 types of receptors. I mean, in Dr. Bazel's notes that there are 2 types of receptors, the L and the T. So the L, as in Larry, type are the only ones available where we have drugs available for. The T, as in Tom, T type is not, we don't have any drugs designed for it. Anyway, so the L receptor has some certain binding sites where these drugs bind to, and they change the structure of the channel such that the channel is blocked and is no longer able to let the calcium pass through. So there are 3 distinct called allosteric binding sites. I hope you still remember the difference between the binding site and the allosteric binding sites. So basically the allosteric are sites where the drugs bind to, and they cause conformation and change or changes to the structure of the receptor such that, in this case the channel, the change in the conformation or the structure of the channel would block the hole indirectly such that the calcium channels are not able to go through. Okay, let's see that in the next slide here. Okay, so this is the receptor, or actually this is the channel where the calcium goes from outside to the inside. So basically the calcium channel blockers, they block the inward movement, the movement of the calcium from outside of the cell to the inside. Okay, they're also known as slow cardiac channels. Anyway, so this is the channel, and you have the binding site for, you have the allosteric sites for the V for verapamil, D for the dialtism, and N, for example, for the nifedipine or nicardipine or any of these for DH, DBHs. Okay, so these are the binding sites, allosteric binding sites. So the drugs bind here, here, or here, not like in the middle of the channel. Okay, so by binding to any of these allosteric sites, they change the structure such that this channel is blocked or closed. Okay. Now, since these products, they affect the same channel or receptor, they do interfere with each other. In other words, if you combine the dialtism with 1,4-dihydropyridines, let's say the nicardipine, for example, if you combine these 2 together, then they enhance the effect of each other. Okay, but if you combine dialtism with verapamil, then they inhibit the effect of each other, and the same with the verapamil. If you combine it with 1,4-dihydropyridines, they inhibit the effect of each other, which is illustrated here in the table. Okay, so because they all work at the same receptor allosterically, they do interfere with each other. So dialtism with any of the 1,4-dihydropyridines enhance each other, while the verapamil with the dialtism would inhibit the effect of each other, and the same with the verapamil with the any of the 1,4-dihydropyridines. Okay, which is again here in the table. The next table here shows a comparison between these drugs. Notice that the verapamil and the diltiazem, they have similar effects, which is different from the 1,4-dihydropyridines. The main change would be on these last three features on the effects of the cardiovascular system. In all cases, both causes vasodilation. So both classes, or all of them, they cause vasodilation, and therefore they reduce the blood pressure. So the major effects, pharmacological effect of these products is vasodilation, which enhances the blood flow and the oxygen ability to reach to the heart, for example. Okay. Now the main difference is the fact that the 1,4-dihydropyridines, they increase the heart rate, and they also might increase contractility. They don't have an effect on the AV conduction nodes. And the reason these 1,4-dihydropyridines, they increase the heart rate and may increase the contractility, the force of how the heart contracts, is due to the sympathetic reflex. In other ways, it's due to the what's called reflex tachycardia. So if you administer these products, they cause vasodilation. I mean, the 1,4-dihydropyridines, they cause vasodilation, and as a reflex of that, the heart try to work harder to supply the blood and resist the vasodilation effect. So it increases the heart rate and the contraction. And these products do not affect the AV or the SA nodes. On the other hand, the verapamil and the diltiazem, they cause vasodilation and reduce the blood pressure, but they also block the SA-AV node, and as a result, they decrease the heart rate as well as the contractility, the contraction of the heart, and through the inhibition of the SA-AV node. Okay, this is the major pharmacological effects between these two. Okay, let's talk about the structure-activity relationship for the 1,4-dihydropyridines. We'll only talk about the 1,4-dihydropyridines structure-activity relationship. We will not talk about the diltiazem or the verapamil. So, as far as the structure-activity relationship, I do not expect you to memorize these, but you should be able to use them. In other words, if you are provided with this information, then you should be able to predict, what effects each change would occur. What if a change occurred to the structure, or how does it affect the activity? So let's go through them, and then if we understand each one of them, then you should be able to predict and apply that in any question you might see. Okay. So the first one says that a substituted phenyl ring at position 4 here, a phenyl ring substituted by any other heteroaromatic ring should retain the activity. In other words, this ring here has to be an aromatic ring, either a benzene or maybe a pyridine ring. And pyridine basically is something like this, but it would have 3 double bonds. Okay, so any substitution of this ring with a similar ring that is a heteroaromatic ring, that would retain the activity. If you replace it with an alkyl group, let's say CH3, CH2, any of these alkyl, whether it's cyclic or non-cyclic, then the activity decreases. So this is point 1 and 2. Okay, and then the next point here is actually very interesting point. Basically says that this ring here, if we substitute, if we add groups at the ortho or meta position, by the way, this position here is called ortho, this is called meta, this is called para position. Okay, so substitutions at these positions at the ortho and meta are very important, as we will see, for the activity. And substitutions at the para position here, would cause the activity to decrease. Okay, it will cause actually a significant decrease in the activity. Why is that? The reason is that we want this ring to be perpendicular to this ring. So in order to make that perpendicular, we could substitute groups at these positions, the ortho or meta, such that this ring is locked into the perpendicular position because it's no longer able to rotate around this single bond. I'm going to illustrate this in the class with some modeling tools kit. So if we substitute these two positions with any function group, it doesn't have to be, by the way, it does not matter the electrical nature of these groups won't make any difference. So you could use an electron withdrawing, electron donating group. It doesn't matter as long as we have a group here that would prevent this single bond from rotating, because it clashes with the substitutions at these positions at R2 and R3 and makes this ring perpendicular. Then the molecule will be active. If there are no substitutions at the ortho and meta, and when I say ortho meta, I also applies to here ortho and meta positions, so that's left side or right side. If there are no substitutions, then this ring is able to rotate and it's no longer locked into the perpendicular position, and the activity significantly decreases. Okay, so and the same if you apply, if you put a substitution on the para position, the ring is still able to rotate because it's not locked into the perpendicular position, and then the activity is significantly reduced. Okay. Okay, the next point talks about this ring here. This is a pyridine ring, but it's actually has one hydrogen added in this position, one hydrogen added in this position, so it's called one dihydropyridine. Now this is the ideal ring. If further oxidation or reduction, in other words, if you add more hydrogens or remove hydrogens, in other words, if you increase the number of double bonds or reduce them, then the activity decreases or could disappear, abolishes completely. Okay, so this is the ideal ring for the activity. If you, for example, add another double bond here or make it a pyridine, or if you remove this double bond and add hydrogens, in other words, if you oxidize the ring and becomes piperidine, or if you reduce the ring further and bring it back to the pyridine, then the activity will be lost. Okay, and then the next point here talks about the ester groups at position 3 at C3 and 5, which is here at R2 and R3. Okay, so the ester group is actually important for the activity, and if they are substituted by a nitro group, for example, then the activity will be lost. In fact, these drugs could become an agonist. They could activate the channel instead of blocking it. That's why this class of medications should be better called calcium channel modulators, because depending on the substitution at position at R2 and R3, depending on the substitutions here, these products could be an activator or an inhibitor to the channel. So in order to make them inhibitors, we should have ester group, and by ester I mean CO double bond O. So COO, anytime you see COO, that is an ester. Okay. If you substitute it with an NO2, for example, then the activity will be switched from a blocker to an activator. So for example, this structure here, we have the isradipine as a blocker, but then if you substitute the ester with a nitro group, it becomes an activator, so it actually enhances the calcium to go through the channel. Okay. The next point talks about the fact that the majority of these molecules, except for the nifedipine, are actually chiral. Okay, what does that mean? if let's start with the nifedipine. If you have the nifedipine, the R2 and R3 substitutions are identical, which means the molecule is symmetric, and therefore because it is symmetric, it will be superimposable to its mirror image, and this will make it achiral. Basically, it is not it does not have a stereochemistry or stereoselectivity. Okay, except for the nifedipine, all the other molecules have a different substitution, have substitutions different at the R2 and R3 positions, or also you could call them at C5 and C3 positions. So these substitutions, when they are different, they make the molecule non-symmetric, and therefore the molecule it becomes chiral, which means you would have one isomer or one enantiomer and another enantiomer based on where these two groups are substituted to the left or to the right. Okay, so and we're going to talk about the importance of this chirality when we talk about the metabolism. Now, the other thing, the last point about the structure activity relationship is that the size of the group here at R1, which is right here, if we increase the size of this group, it would enhance the potency. In fact, all the molecules except for the amlodipine have CH3, which is a small group here at R1. Now with the amlodipine, when we increased the size of the R3, the R1 at this position, the potency increased, which means that there must be some binding sites here at the receptor that enhances the potency or the affinity of the drug. Okay, so this completes the SIR for this class of drugs. Just make sure you understood each point, such that if you see this page in the exam and you have some questions about the effect of any modifications, you're able to use it. Okay. Okay, next let's talk about the metabolism of these calcium channel blockers. All of these calcium channel blockers undergo an extensive first pass metabolism by the enzyme CYP3A4. In fact, they inhibit the enzyme, which would be responsible for a lot of the side effects. I mean, the drug-drug interactions. Okay, because this is a common metabolizing enzyme. There's an exception to this rule, which is the clevidipine. It's actually basically metabolized through the hydrolysis, ester hydrolysis. Okay, if you look at the structure, it has an ester group that is hydrolyzed, and that's how this drug is metabolized. And in fact, it does have a short duration of action, which makes it perfect for IV infusion. Basically, you could control the amount of the drug immediately by administering the drug or stopping it, so you have a better control of how much block into the muscle, to the cardiac muscle, you want to have during a surgery, for example. Okay. Also, you could also control you have a better use for this drug in case you have a renal or hepatic dysfunction, because the drug is metabolized by the esterases, which are available everywhere in the blood, in the tissue, so it could be basically metabolized without relying on the hepatic metabolism. I still think it would have to go through the renal to be metabolized, so I'm not sure why it wouldn't matter for the case of the renal dysfunction. Anyway, so the clevidipine does not need a dosage adjustment unlike the others. The next is basically verapamil. When it's metabolized by the N-demethylation, which is an oxidation process, will result into norverapamil. And by the way, anytime you see nor, it means there is no CH3. So you remove the CH3 and you have norverapamil, which is actually an active metabolite. And it could actually exceed the plasma concentration level of the verapamil. So you have two active products of the verapamil and its metabolites. Okay. Something else is also important about verapamil, which is the fact that the S isomer for verapamil goes through an extensive first pass metabolism. So when you take the drug orally, then the S isomer, not the R, the S, will go through extensive first pass metabolism, and that's why you'll need higher dosage of the verapamil if you take it, if you give it orally. Now, why this is important? Because if you decide to give the verapamil by IV, then you're not gonna need as much higher dose as the case of if you take it orally. The reason is, of course, because if you give it an IV, then you don't have to worry about the first pass metabolism, so you basically adjust the dose such that you don't need as much um, of the verapamil if you give it by IV. If you give it orally, then you will provide higher dose. If you give the same dosage IV, let's say you give the same amount of the drug IV as you give it orally, then you will have higher effect of the verapamil, prolonged PR interval on the electrodiagram, which means that the block of the channels, block of the conduction of the heart rate will be longer. Okay, so just something to keep in mind. Okay, next let's talk about some pharmacokinetic parameters. The nicardipine and verapamil should never be given in an IV solution that contains a sodium bicarbonate or any IV solution that has a pH higher than 6. The reason is, if you do that, these products will precipitate. If you remember in your class with Dr. Gnasilan, the importance of the pH on the drug's ionization and anionization. So if in this case, if the drug has if the pH is higher than 6, these products are not going to be dissolving, they will be precipitated. Okay, the same thing applies if you have what's called the lactated drinker solution, which is used in the IV bags. So you should never administer nicardipine with that, because the pH for that is 6.5. So anytime you have a pH that's higher than 6, there's a chance of precipitation. Okay, so for both nicardipine and verapamil. I'm not sure if the same applies to the verapamil, but it does say here that's okay. So Dilzim in theory should have the same problem, but there is not enough studies to prove that. So I'm not sure about the verapamil in the case of the lactated drinker solution, but the basic rule, it says verapamil will precipitate and lactated drinker solution will have pH of 6.5. So again, it should be the same thing applies to the verapamil. So any of these, nicardipine, verapamil, or Dilzim, should be avoided in the case of lactated drinker solution or any preparation that has the sodium bicarbonate, which would cause an increase in the pH. Okay. Another important parameter to keep in mind, pharmacokinetic parameter to keep in mind, is that these calcium channel blockers, the short-acting ones, should be formulated in the sustained release formulations. Why? Because if you use the immediate release, then this can cause like a sudden or a fast vasodilation, which can result into myocardial infarction. So these products should always be formulated into the sustained release formulation, such that they are actually released in a smaller amounts, okay, as compared to being released all at one time, and then that causes sudden vasodilation, which could cause myocardial infarction. And I'm sure you have seen this in the pharmacy. You always see the Dilzim in an extended release, nicardipine in extended release. Okay. Finally, let's talk about the side effects and the drug interactions for these products. Many of these side effects have to do with its pharmacological effect. Basically, you have a vasodilation, which leads to edema, flushing, hypotension, nasal congestion, headache, and dizziness. In fact, these side effects will go away with time. Among the other side effects, especially with the dihydropyridines, are actually the ones resulting from the reflex tachycardia, resulting from the sympathetic response to the vasodilation. So when you have a vasodilation, again, as we explained in the first slide or two, palpitations and tachycardia will occur as a reflex to the vasodilation, and this will cause the side effects of the chest pain and tachycardia palpitations, which are not seen in the verapamil and the delsin because they block the SAVA nodes. Okay, so another way to avoid this side effect is by giving a beta blockers, but then, however, the use of beta blockers can further depress the heart, and so it should not be used with the calcium channel blockers. And I want to point out that I'm talking about mechanism of actions here, but for the exact application of these products, you'd have to check with the clinical faculty as far as what are the best cases, whether you should combine them or not. Okay, I'm only concerned about the concepts here. Okay, so like we said, then with the verapamil and diltiazem, they actually besides the vasodilation, they block the AVSA node, so they do cause bradycardia, which means reduce in the heart rate as well as the heart force. Okay. Now, next, I want to talk about some contraindication for the use of clevidipine. In the case of clevidipine, it's formulated in the oil and water emulsion, which contains these products. So if somebody is allergic to the egg, then should be avoided. Finally, we have talked about the side effects that, or the drug-drug interactions that could occur due to the inhibition of the cytochrome P450-3A4. So we will see the table next that shows these interactions. So there's plenty of drug interactions between these products, calcium channel blockers, and the drugs that are metabolized by this enzyme. In addition, there's an interaction between these products with the grapefruit juice. So basically, the grapefruit juice can affect the enzyme, the cytochrome P450, and since these products are extensively metabolized by this enzyme, then this can affect the plasma concentration for these products. So just as a reminder, the grapefruit juice actually inhibits the cytochrome, the CYP3A4, and therefore by inhibiting this enzyme, these products will have higher concentration in the blood. Okay. Finally, this table is just for your own reference. I do not expect you to memorize any of this. I'm only concerned about the concept that these products, the calcium channel blockers, they affect the CYP3A4, and any of these products that are metabolized by this enzyme will therefore be affected. Okay, so this is just for your own reference. You could go back to it if you need it, if you ever need it.